are the group that will be presenting on our algae-based biofuel refinery. I'm Kevin Kinnaman. This is my partner Nolan Sue and my other partner Brian Wolf, and we hope you enjoy the presentation. We'll be beginning at this point. Please save your questions until the end. So, we've noticed a couple problems in the industry these days, primarily in that despite the rapid advancement of green fuels in the industry like solar panels and hydroelectric power, there is still a need for a transportable liquid fuel. Cars, jets, and boats still rely on this to get fuel. It's difficult to put a solar panel in a car still. So we're hoping to find an advanced form of biofuel which can act like diesel but doesn't have the issues of modern petroleum. It needs to have a positive impact on the environment, it needs to be renewable, it can't compete with foodstuffs, and if possible, we need to make it as cheap and efficient as possible to make so that there's a good profit margin to encourage development. The current dilemma as it stands is that petroleum, as mentioned, isn't the cleanest resource in the world. Not only in its burn, but also simply production of petroleum is a CO2 positive process, releasing a fair amount of pollution to the environment. And additionally, there's currently not much else we can use for portable liquid fuel. It's just, there's limited options right now. However, biofuels from, say, corn and sugarcane have come into the field, especially ethanols and gasolines. We're hoping, however, that we can find a method which doesn't compete with foodstuffs, because every crop dedicated to corn or biofuel which isn't going into food, is that thing automatic?
No.
All right. Which isn't going to food is obviously causing trouble. So our solution is algae, and we'll be giving you a quick overview of how the algae works.
So as Kevin just said, our solution is to use an algae feedstock, or as the feedstock, to produce a biofuel, specifically biodiesel in this case. So how it works is that algae is grown in a mix of phototrophic and heterotrophic processes. In this, it produces an oil. The oil can then be extracted from the algae cells and refined and converted into biodiesel. This biodiesel can then be sent to a refinery, refined, and then eventually sent out, sold to consumers. The profit for a process like this can be improved by government subsidies, specifically renewable index numbers, which we will go into detail on later. So, how do we get diesel from algae? Again, as we said, algae are plants. They're basically small plant-like organisms which can produce an oil. For our specific species of algae, there are many kinds, obviously. We decided to go with Nanochloropsis as our specific strain. The reason for this is a number of reasons. First of all, this strain of algae can be processed both heterotrophically and phototrophically, so by a photosynthetic process or a metabolic process. In addition, this specific strain of algae has a rather high lipid concentration per dry algae mass, which is obviously ideal considering the lipids are what is going to be converted into our final biodiesel product. So as far as the kind of lipids that we're looking to get, algae store their energy in a form of lipid known as a TAG, or a triacylglyceride. You can see a picture of what the basic of this model, or of this molecule, looks like. And basically you just have a glyceride molecule with 3 long-chain fatty acids attached to it. It's these long-chain fatty acids that basically comprise biodiesel, so when you convert it, you basically remove the glyceride molecule, and you're left with your long-chain fatty acids. Oh no, never mind, you're good. I lied. And the long-chain fatty acids are going to be between C18 and C20, because this is what matches a comparable cetane number for diesel fuel, and we want to mimic that. Okay. So this is a basic schematic of what our process is going to look like. There are 6 main process steps. We begin with algae growth in a phototrophic bioreactor. Again, this means that it uses the photosynthesis reaction, which we all know from Bio 101. It's light, CO2, and water combined to grow the cell. After this, we move on to a heterotrophic bioreactor, which uses a metabolic process. So it uses sugar and oxygen to grow the cells. And the specific focus of this part is going to be the lipid growth. After this, the algae must be dried. We have 2 processes for drying. One is a bulk water removal by electroflocculation, and the next drying process is sort of a fine water removal using a continuous tray type dryer. The goal of this is to remove the water concentration down to less than 1%, and this is important because in the later extraction and conversion steps, Having water in the system will lead to side reactions, which we don't want, forming soaps and things like that. So after the algae is dried, we send it to an oil extraction step, which basically involves a hexane solvent to remove the oil. And after that, the oil is sent to the final step, which is the conversion to biodiesel by a transesterification reaction, which is a common process used to convert any oil into biodiesel, including vegetable oils, things like that.
So I'm here to talk to you about the business plan. The most important part, how are we going to make money? Currently, algae-based technologies is inefficient. The heating process alone is extremely energy inefficient. Therefore, the cost to produce it does not outweigh the amount of money that can be made off of it. The way we're going to alleviate this is by combining with ExxonMobil at an oil refinery. With an oil refinery, we're provided with off-streams that they have, so heat, CO2, and water, as well as the expertise in land that Exxon can provide, while we're providing them with their own bio-renewable energy source, which kind of cuts down their cost of production as well. Our process currently produces 1,000 barrels per day. The reason we chose 1,000 barrels per day is that at 1 barrel per day, it's useless for the oil refinery. But at 1,000 barrels today, we still maintain our pilot plant scale while giving a good amount of data to ExxonMobil. We hope to reduce costs by improving operational costs from ExxonMobil and then improve our sales of bio-renewable energy. So with that being said, welcome to Baytown, Texas. Baytown, Texas is where ExxonMobil Corporation largest oil refinery is located. And we've chosen Baytown, Texas for a couple of reasons. First of all, as we said, Exxon can provide that infrastructure and support that we need. Secondly, Texas has kind of a climate that stays the same throughout the year. We don't have to worry about any tornadoes or earthquakes too much. So we can easily create our equations to monitor all of our growth and our processes. In addition, the weather, as I said, is consistent. So the sunlight for the algae will be consistent, and we'll be able to actually grow at a rate consistently throughout the year. In addition, if you look back here, we're on a port. And that port will provide us transportation, which, as you know, or as some of us know, transportation is a large cost in the industry. If we're able to just take the transportation costs down, then once again, we remove operational costs. So we'll go into a few specifics here for our business model. The actual growing process of algae requires three things: water, CO2, and nutrients. With the CO2 being one of the more expensive feed sources, it's imperative that we can use the oil refinery's CO2, as they have a ton coming off just from their process. This will cut down the operational costs of growth and give us a little more boost in production. In addition, the oil refinery produces a lot of heat. It's one of their off-streams, one of their byproducts. Unfortunately, we can use that in our heating cycle to kind of dry the algae, as Brian spoke about earlier, while not costing a fortune. And once again, we have the location of the ships and the docking, and Exxon has people, expertise, and experience to spare for us.
At this point, we'll be starting with a quick technical summary of our process so you can understand the details of what goes on a little bit better.
Okay, so perhaps the largest portion of our process comes with the bioreactors. So the point of the bioreactors obviously is to increase the cell count, grow the cells, but then in addition to increase the lipid concentration, because obviously it's the lipids that's going to make up our product. So the first phase of growth, if you remember there are two phases, is going to be the phototrophic algae growth. And again, this is focused on the algae growth portion. So how it works, it's a photosynthesis process, so light, CO2, water, and some other nutrients in there for the cells. The important thing here is that it's a carbon negative process, which is a rather important sort of intrinsic benefit that we're looking for. As far as growth medium is concerned, we've been following a Redfield ratio for our calculations, which is basically just an empirically derived ratio of carbon, nitrogen, phosphorus that can promote optimal algae growth, really. And basically at the end of the day, we expect over a residence time of 6 days to get an algae growth in the reactor of over 9 times by weight. After this point, the algae are then transferred to the heterotrophic growth phase, with a small portion being left in the reactors to seed the next batch of photoreactors. Go ahead. So the next part of the growth is going to be, as I said, a heterotrophic process, which is a metabolic process. So basically, instead of light and CO2, you use sugar as your carbon source and oxygen to promote growth. The key here is that the heterotrophic process is focused on increasing lipid concentration, and how it does this is by removing the ammonia. So it's been shown that if you starve the cells of nitrogen, you actually inhibit their growth, at which point they take the energy and convert it into lipids instead, because I can't grow anymore. So that's what we're doing here. And basically, our outlet concentration that we're looking to get is 150 grams per liter. That's pretty standard, found in the literature, and we can do this over a residence time of 1 day, we found. Go ahead. And so these are just some visuals so you guys can see what we're talking about here. Here you can see a picture of a phototrophic bioreactor. Obviously, they're usually made out of glass to allow light to penetrate through, and they often have, the cylindrical shape is really to maintain a high surface area to volume ratio. Again, so that you can get a lot of light to penetrate through there. You usually don't see reactors any larger than 20 to 30 centimeters in diameter, really. So then, after the phototrophic part, they head over to the heterotrophic part, and here we see a small schematic, really, of phototrophic leading into the heterotrophic reactors. The heterotrophic reactors are simply just steel tank batch reactors, really. They can be large. Surface area to volume doesn't really matter. And just to give you guys an idea of the scale we're talking about here, in order to achieve 150 grams per liter concentration at the outlet over our 7-day period, we calculated that the reactor volume is going to need to be on the order of 28,000 cubic meters, which is kind of a lot. And based on the literature and stacking and organizing the batch reactors, we find that to take up an area of about 70 acres, which sounds like a lot of space, but compared to alternative methods using vegetable oil, corn, things like this, it's almost a full order of magnitude more efficient per acre, the biodiesel that we're getting out of it.
So the next step that we've determined is the drying process. And the drying process will be done in 2 phases, the bulk water phase and the fine water phase. So for the bulk water phase, we messed around with a few ideas. Centrifugation and filtration came up. Unfortunately, nanochloropsis is a very small molecule for algae. It's on the nano scale. So filtration, there's no filter that can take our mass coming out per day with being durable enough. And centrifugation would be a huge capital cost to invest in. And if that breaks, our system has to shut down. So what we've chosen is an electroflocculation process, also known as electrocoagulation. It's a rather simple process. What happens is a small charge density is applied to a batch process, which causes the algae to aggregate together. Once it's aggregated together, the water can either be siphoned off, or you can scrape off the top of the algae if it's rise to the top in a slurry. Now, this net charge can be dangerous, so our process will be grounded after it's performed. However, it's a bulk water process that removes about 90% of the water, and we've determined that it will take about 12 batches to perform per day. And if we do this staggered, so 30 minutes per batch, 15 for the electroflocculation, 15 for the removal, that we can run this in about 6.5 hours for operating time. The next station we go to is the continuous tray dryer. So at this point, we have to do fine drying, removing that 10% left in the algae. We've determined that we don't want to do this in a batch process because that would be inefficient, doing process after process per day, and will be time consuming. So what we've chosen here, as Kevin likes to refer to it, as baking our grains. So the baked greens process is the continuous tray dryer. And as you can see here, it's kind of like baking a pizza. You've got a bunch of conveyor belts moving along for the algae that's put in continuously, and heat will be applied. Now, this heat is from the oil refinery, from their off streams. This off stream will, again, cut our oil refinery costs from the 820,000 kilowatt hours per day that we may have to incur as an expense to about 0, because we can take that as an off stream. This also provides a low residence time and is very, very effective in drying our algae. We'll go into a few controls later on, but basically this process removes up to about 1% left of the water.
Thank you for that color commentary, Noah.
You're welcome.
Once we have dried the algae properly, we then need to actually get our hands on lipids. That's why we grew the algae in the first place. The easiest way to get the triacylglycerides out of algae cells is through the dissolution in hexane. Hexane, due to its chemical properties, at about a 4.5 to 1 ratio with the algae by mass, will actually cause the lipids inside the cells to dissolve and become part of the hexane solution, but leave the algae husks behind. That's called a micella. Once the algae biomass settles due to its comparative density, we can actually just drain out the hexane solution and boil it off relatively easily in a distillation column. This will give us a 93% yield of our lipids by mass from our algae, which is quite excellent from what we've compared to the literature. And by recycling the hexane, we can keep our hexane prices comparatively low. Once we've got our hands on the lipids themselves, we then convert it directly to biodiesel. This is through a process called transesterification. This is the industry standard method. It's very well documented in research, so we don't have to worry about it being too novel or requiring overly creative solutions. Basically, by immersing the lipids in an excess of oil, of alcohol, and about a 4 to 1 ratio of ethanol to oil by mass, we're able to break off the fatty acid chains from the glycerol head and get our hands on raw hydrocarbon. The hydrocarbons are a primary product, of course. The glycerol heads and the husks can then be sold as a co-product, and through this process, we can get about 96% purity in our biodiesel. This is, again, quite good compared to what we're looking for. There are, of course, some safety considerations to take in mind, which we have covered in a limited degree earlier in the presentation. First of all, the electroflocculation chamber involves placing an electric charge through water, which is very dangerous to your operators. Thus, we're going to design it in such a way that it's very hard to do anything bad to our operators, and we're going to try to automate the system to the degree that we can so that operator involvement is minimal, especially manual involvement. The same goes for our drying chamber, which is effectively a very large oven, and we don't want people inside our oven while it is on. Emergency cooling systems will also be included so that in case there is something terribly unfortunate in our plant, we're able to respond immediately. The largest issue we faced was hexane in our separations process. Hexane is both acutely toxic and excitingly explosive, so we need to make sure that our process is very well sealed and very well maintained at cold temperatures so that the hexane is never at a location or in a concentration in the air that's hazardous. We've actually taken some looks into alternative solutions as well, which we'll describe later in the presentation. One special safety consideration is actually keeping the algae safe. We need the algae to be relatively pure in our streams because if it's not, there could be all sorts of problems with side reactions and with purity levels. As such, we keep our phototrophic and heterotrophic growth systems as closed as possible, and we make sure that our operators don't get involved with the algae as much as possible because operators are contaminated as well. And one big thing is that we regularly clean our system with a caustic solution. This is absolutely essential because if the algae is allowed to get contaminated, that's bad. But what's even worse is if a mutation is allowed to develop. If we get a mutated strain, we not only lose that batch of algae, but we will lose every batch of algae which would be derived from that batch after the draining process. So we need to make sure that genetically our algae remains safe as well. Finally, we've got some analysis of how we could scale this thing up. For the most part, our system can be made larger, but our algae crops do have to be mostly multiplied. It's difficult to simply make larger tubes because those will reduce the surface area to volume ratio. But we found that based on the literature, we can expect to be able to scale this thing up to as many as 700 or 1,000 acres in order to make it commercially viable. Some systems could also be expanded or made slightly redundant. If we wanted the continuous tray dryer to be larger, that'd be easy, but if there's enough money free, it might even be possible to have 2 of them so that in case one fails or needs to be shut off, the process can continue indefinitely. Also, this actually makes us more profitable at commercial scale because many of the functions and processes in our plant have high capital costs, but the operating costs are fairly stable, especially operators. Individual operators can actually manage fairly large systems and fairly small systems at about the same efficiency, so long as we're careful about how they're managed. To this end, we believe that a commercial scale system can be done quite easily so long as the money is available. At this point, we'll begin talking about controls and testing.
So, as Kevin said, I'll be talking about controls and testing here. One of the things that we were presented, or a challenge we were presented with, was continuing our process continuously. We want to reduce the amount of operator or manual labor needed for this. So we put in some controls and parameters that will need to be controlled automatically. First of all, the bioreactor, the nutrient feed flow rates. So we can monitor the amount of lipid growth and the amount of growth in the algae, which will allow us daily to change the nutrient feed flow rates to get our desired algae outcome. Secondly, the drying process. While the electroflocculation may need to be monitored a little bit, what we found is that the charge doesn't actually vary that much. You can put a smaller or a larger charge, and the most important thing is to keep it safe. So we won't be monitoring that much. What will be monitored is the heat generation in the continuous tray dryer, and I'll go into that a little bit in the next slide. Secondly, the extraction process with the hexane. We don't want the hexane to overheat and cause an explosion or cause some injury to our operator, so we will be monitoring the heat in those batch reactors. As for testing, we'll be testing the lipid concentration and chain length just to ensure the productivity and our product are actually what we say that they will be. We don't want to be promising a product that we can't deliver on. So we'll be testing turbidity, and this will be tested during the growth phase and post-extraction. So going into controls. So the controls will be done on our dryer. To control our dryer system, what we'll be monitoring is the mass of the water inflow, which will be our load variable, the mass of the water outflow, which will be our controlled variable, which means our manipulated variable is actually the heat cycle. As you can see here, it's a rather simple system. We've determined that there won't be gains from other parts of the system, mostly because this is an off stream from the oil refinery. When we did our analysis of the process controller, so the PID, we determined that a proportional controller would actually be most beneficial. When we did the numbers, the integral and the derivative controller actually were to the scale of about 0.0042, which would be really inefficient, and the capital cost would not be worth the control that we were given. So we've chosen a proportional controller. As for the valve that controls the heat, it will be a fail to close. This is already a stream that is a waste stream for the oil refinery. We're just taking an off stream. The worst thing that can happen is if we have too much heat coming into our system, overheating what we have going on. So it's going to be fail to close, which will just go to the waste stream for our system. In addition, this will be a feedback controller measuring the water content in the system, as opposed to a feed forward or a cascade. It is possible to make this feed forward or cascade, but that requires a math model that we simply do not have the math or the data on to create.
Just moving on to a quick economic summary.
So before we dive too much into the numbers, I want to talk about a brief point or a topic known as RINs, or Renewable Identification Numbers. This is important to us because this is related to the legislation and government subsidies regarding biofuels. So what RINs are is basically the EPA's method of controlling and basically enforcing the biofuel legislations in the United States. So the RFS, the Renewable Fuel Standard, basically requires that every year companies mix a certain percentage of their fuel with biofuels. And RINs are the way that the EPA kind of tracks and checks and makes sure that everyone is producing the amount of biofuel that they need to produce. So how it works is that every gallon of biofuel has a RIN associated with it, and at the end of the year, those have to be turned in to match the quota of the company. Now, how RINs are structured is kind of funky. They can actually be traded and sold between companies. So if you're stockpiling a bunch of RINs, you can sell those actually to other companies. And because of that, it's actually, the RIN is basically a commodity item now that has a price associated with it. And we can actually utilize this because we'll be generating excess RINs because we are a green technology, so we can actually generate 1.5 RINs per gallon of fuel, so we can make a profit from these excess RINs to help with the profitability. So for fixed capital cost estimation, we used an order of magnitude analysis, which is basically plus or minus 40% on this. There were two methods. First, we compared our capacity to existing biofuel pilot scale facilities. So we basically took their capacity and their fixed capital cost and used that compared to our capacity to kind of extrapolate a fixed capital cost from that raised to an order. And then the second method we used to check this was based on our major equipment costs. So based on Perry's handbook, tables found in there, we found the cost of all of our major pieces of equipment, the reactors, the dryers, the distillation columns, which you can see here is $8.5 million. And then based on Guthrie method factors found in there, you can extrapolate out the total fixed capital cost from that. So basically we came up with, I think it was $52 million for our fixed capital cost. Okay. Here's a list of what we came up with for operational and variable costs. As far as operational costs are concerned, we came up with what we thought would be a reasonable number of process shifts to run the facility, number of operators basically. And then we were able to use factors from Perry's to find the maintenance, payroll, those other sorts of things from there. As far as raw materials costs are concerned, those values came from stoichiometry, the literature, and our own material balances. And for utilities costs at the bottom there, those came from our own energy balances around the specific systems, mostly the dryer and the separation. The total variable cost that we came up with is $76 million. This is a worst case scenario where the refinery says, okay, you guys are on your own, we can't really support you, so we would be paying for all of our CO2, all of the utilities, we wouldn't get any spare heat from them. So if you look real quick at the utilities, the drying is $20 million, which is kind of a lot, and CO2 is $10 million a year. So if we can get support from the refinery on those, it can drop our variable cost. Go ahead. So now, as far as the cash flow is concerned, we have four main sources of revenue. Those are the biodiesel, the RINs associated with the biodiesel, the glycerol that's coming out as a bottoms product from our transesterification reaction, and finally the dried spent algae husks from the extraction. Our total revenue we came up with was $82 million. So based on straight line depreciation, 15-year useful life, taxes, all that jazz, we come up with a gross profit of $4 million, payback of 13 years, and about a 2% IRR, internal rate of return, which sounds good because we're making money. That's always good. But unfortunately, since working cost of capital in the industry is between 6 to 8%, that's really not all that good. We're not really up to par. Again, this first figure here is based on worst case scenario where we are basically our own separate plant. We're not getting any support from the refinery. Now, if we consider that we can utilize waste heat streams from their high temperature processes, our processes for drying are relatively low temperature in comparison. So it's not unreasonable to assume that we can get about a 50% reduction in utility cost for just the drying. If we assume this, then our gross profit jumps up to $10.5 million, and our IRR is 19%. So basically, if you get nothing else from this slide, just understand that without the combination of RINs and support from a refinery, this isn't profitable. Go ahead.
So now, turning back to the scale-up ideas, once we've got all this profit in mind, there's always the fact that if it is profitable, it might be more profitable though commercial scale. As we mentioned earlier, for the most part, it's the capital costs which go up with scale. You have to build more machines and build them larger. However, there's a comparatively small operational cost increase owing to the fact that for the most part, the resources can be reused and recycled, and there's not a tremendous increase in paying your operators because you have the same number of them managing larger but not necessarily more complicated machines. For this reason, we believe that a commercial scale up could be possible and highly profitable if we went up in production by about 10 times to 10,000 barrels per day. We also have a couple of alternative considerations such as technologies and future economic incentives. We didn't immediately come up with this particular combination of technologies for our system. We had a few other ideas. A mixotrophic growth process in which the sugar feed happens at the same time as the light feed was considered. It's generally considered more efficient, but right now it's very difficult to balance that with commercial scale algae production. We couldn't find any literature suggesting that it was easily done or easily managed. We could also, instead of using hexane to separate our oils, use membrane separation or use heptane, which is significantly safer. There are a few issues with each of these, which is why we went with hexane, mostly the fact that it gets the highest yields. Heptane works faster and is safer, but its yields are disappointing compared to hexane, so it would need a more advanced system to get the same output. Similarly, in order to keep our price advantage, especially once we go commercial scale, we need to have a few different ideas. One of them is that we could patent our design and license it to other companies so that our plant would be repeated multiple times across the country and the world. This helps make sure that we remain profitable. Other options is to make sure that going commercial scale could potentially drastically increase our profitability and help with this keeping us economically viable even as the system advances. Finally, the biggest thing that would help us a lot is qualifying it as an advanced biofuel. There are a number of legislation issues with this right now, but if it does come through, that will increase the number of RINs we get per gallon, again, increasing revenues and profits.
Right, just some final thoughts. We did just throw a lot of information at you, and I know it's hard to absorb it all at once. So what we're going to do is we are going to take a currently non-profitable technology in bioalgae, combine it with an oil refinery, and produce at 1,000 barrels per day to become profitable by reducing operating costs and kind of having that partnership.
We will utilize the partnership in combination with United States regulation in the form of RINs to help make this profitable.
And lastly, if everything goes well, our design will give us a clean, renewable source of biodiesel which can help alleviate global demand for a transportable liquid fuel. Does anyone have any questions? And I don't know why I was doing that all the time.
Wasn't so bad.
So, in all seriousness, does anyone have any questions?
No questions is great, too.
Yes, Professor?
Easy one. What's the price fluctuation for the ring?
We actually have a chart of that in our...
So the price fluctuation, I'm going to go into a little background here. So the EPA, it's usually consistent with kind of spikes during year of close. So at the end, people are scrambling to grab the certain amounts of RINs that they haven't made throughout the year. So that's when the price actually fluctuates up. However, there have been some issues with the EPA. In fact, the EPA determined that there's less of a demand, only 2 billion gallons worth of biodiesel for algae. So currently the price is at $0.75 per RIN each. We expect that to fluctuate higher throughout the oncoming years, but that is our current one for the past year and a half or so.
Just to give you an idea, I believe in January or December it was up well over $1, at like $1.40 or something like that. So it fluctuates pretty drastically.
What was the temperature of your dryer, and would you ever consider like air drying your product to save utility costs if you didn't have the streams from another plant?
So currently we're drying at about 100 degrees Celsius, just the evaporation temperature of water. We have looked into other processes, so air drying, and we found that that's inefficient, but it would be more efficient than actually using a heat stream if we had to pay for it. This is kind of the problem that people are running into with algae. The drying process takes a lot of energy, which makes it so inefficient. So we've looked into that currently, but as of now, it isn't a viable option.
We actually checked the literature for alternative drying solutions. While some of them work well at the lab scale, commercially there was really no method that was presented beyond you have to expose it to a certain amount of heat energy over a certain time. And whether you leave it out sitting in the sun for a week or bake it for 1 hour, eventually the energy has to be given.
Yeah, the issue really is time. If you remove the heat, it's going to take a lot longer and slow down the process. So you need to have more capital costs, more dryers or something like that to make up for it. So.
Any further questions? Julie?
What inspired you to take this on?
Well, the prompt was a big help. It was varied. As I recall, this is thinking back almost 9 months at this point, part of the reason that we were interested in it was we couldn't agree on what we wanted to do at first. And
That's true.
as I recall, we kind of all realized that we had a little bit to do with this one. We'd all been involved in something green or something petroleum related. So we figured that since none of us could really make our various co-ops work together, we figured let's do something that none of us have really gotten involved with, and let's at least make it something interesting. And a couple of us had some contacts in the industries that really helped us decide, oh, well, we can call these people or those people.
And green energy's the hype. So we're just sheep.
Don't accuse us of creativity we didn't have. Anything else?
Could this potentially be run independent of the oil refinery? Like, could it potentially get big enough that you would no longer need the refinery's resources?
So that's a great question, and for that we kind of have to go into government regulations. As we said, this is a very inefficient technology at present time, and there are definitely people more qualified than ourselves looking into the technology. If the EPA does determine that algae is the new energy source, the new standard by which we should produce all oil. Then this would absolutely be economically viable, and we could do this independent of anyone. And we could scale it up as we've been talking about. Again, that is reliant on the government, which unreliable, but to answer your question, yes, depending on circumstances.
And I think Kevin mentioned it in the slides too. I mean, everything scales up better with, scale.
Right.
So, any bigger producer than those people.
So if that's all.
18% IRR for renewable energies. Biofuels. It's great.
We were impressed too. That's what kind of got us excited. Was like we thought, oh, this is physically possible, because one of the big things we saw in literature was a lot of people are doing it, and a lot of people were saying it works great as soon as you can make money off of it, which no one could do. So that's anything else, or?
Thank you so
All right.
much.